So 3/4, right? You probably know that as a decimal, that's 0.75. And then to convert it to a percent, you can either multiply it by 100, or you can just move the decimal place to the right too. So for instance, you can do 1 boop, boop. And so this is 75%, all right? Because remember, percent is just the same as saying 1/100, right? So however you want to think about that is valid. If you're given a percent and you want a decimal, you just do the exact opposite. So I'm going to move the decimal point, which is right after the 5, to the left twice now. So I get 0.45, right? So you can think of, again, you can think of it like moving the decimal place by 2. It's kind of hard to see because it's tiny. Or you can think of it as dividing it by 100, right? So again, this is the same as 45 times 1/100. And of course, that's the same as that, all right? So any way you want to think about it. And then these other two are just the same kind of thing. So for 2.19%, you just, the percent symbol again is 1/100. So this is 2.19 times 1/100. And if that wasn't, if you're not clear on what to do there, you can even plug it in your calculator, right? So there's always ways to do these things, multiple ways to do these things. So 2.19 divided by 100, it's 0.0219. 0.0219. And that's the same thing as moving the decimal place to the left too, right? Sorry, right. I don't think you can hear the beeps from my texts, but if you can, I apologize. Any questions so far? All right, and again, sorry?
I'm sorry.
Yeah.
I was just wondering what's the 1/100 again?
Oh, so the percent symbol, all it means is 1/100.
Oh, okay. All right.
Yeah. So like,
I gotcha.
So for instance, to convert 45% to a decimal, you just plug in 1/100 where you see that symbol.
Oh, I see. Okay.
Yeah. It's just notation. Yeah. And then finally, this one, we do the same thing like we did the first one here. So I'm going to move it to the right two places. And so just be careful when you move it to the right and there's nothing here, like it's an empty space, but you assume that a 0 is there. So this is the same as 80%. Right? And again, so that when you move to the right twice, the decimal place is after that empty space. So that 0 is there. All right. So we can go back and forth. So whenever you see a percent, just know that if you're using it in a calculator, you have to essentially convert it to a decimal first, because most calculators don't understand percents. Some do, I think. I think some have a percent symbol, but I've never used it. All right. And now some actual computations with percents. So when you say what is 20% of 145, for instance, all you're doing is multiplying 20% times 145. So it's 145 times 20%. And again, 20% isn't something that you can really plug in your calculator most times. So you need to convert it to a decimal, and then you can plug that in your calculator. So this is just 145 times 0.2. Right. And that's not something you can do without a calculator. So 145 times 0.2, 29. It's a nice number. Look at that. All right. So 29 is 20% of 145. Right. And then this next question is just almost exactly the same question. It's just worded differently. So what is the sales tax on $295? If the sales tax rate is 8.75%. Again, percent, so you need to convert to a decimal and then multiply it times 295, because what you're doing is you're just taking 8.75% of 295. So I'm going to do 295 times 8.75%. Again, I want to convert it to a decimal so I can actually compute it. And again, the same way like we did this one, we just moved the decimal point to, just like we did for these two, we're going to move it to the left too. So, boop, boop. So what is it, 0.0875? And then that again, you just plug in your calculator. 295 times 0.08, oops, 875. and we get something not as pretty, $25 and $81, say. I'll round it. Okay. So again, just quick review on percentages, which we started with. And as I noted before, in the next unit, we'll do more with percentages. This is kind of just what we need for now. All right, so that was the first little group. Let's just do a few more. So we talked about percentages last time, and we also talked about absolute and relative change. So remember, absolute change is just how much a function is growing, like exactly, like the literal change in that function between 2 points is the absolute change. So in this case here, I have a bank account, and in March I had about $1,200, and in April I have $500, give or take. So the absolute change, as we talked about, will just be the difference, right? So it's going to be the 1,200. So maybe I'll say the new minus the old, actually. Right. So whatever the new value is minus whatever the old value is. In this case, the new value is the 512, actually, or the 502. And the old is the original, 1234. Right. And so again, you just compute it in your calculator. So 502 minus 1234. So the absolute change is minus 732. All right. So again, it's just literally the difference between the new and the old. The relative change is more interesting for us, and as far as exponentials go, like we talked about, the relative change is going to be the new minus the old, and then over the old. I think last time I called the old the reference value, but it's the same as I think I pointed that out. So in this case, it's minus 732 over the old, 1, 2, 3, 4. Right. And technically speaking, this is an answer. It's not a good answer though. Usually when you talk about relative change, you want something as a decimal or percent because it's kind of more intuitive, right? So here, for instance, I can compute the relative change. And so as a decimal, it's minus 0.59. But as a percent, I can just multiply it by 100 to get the percent. So it's minus, I'll round it to 59%. Okay. Right, so absolutely, your bank account lost $732, and relatively, your bank account went down 59%. Right, so compared to your initial value of $1,234, you lost 59% of that. Lost, I should say, spent. Right, you spent 59% of that. All right, questions, concerns? Right. And then this last group, this is just some computation. We talked about exponential functions. We defined them to be really anything, remember, of the form f of x equals a b to the x, right? Where a and b are real numbers. A can be anything, but b we took to be non-zero, not equal to 1, and positive for the sake of simplicity. But in any case, in this problem, I just want to plug in some numbers to kind of jog our memories and how to plug things into these functions, because we'll need to plug things into exponentials frequently, right? So for f of 0, I'm just going to plug in x equals 0. So I get 28, 1 point, in this case, 393, and then to the 0. What is anything to the 0?
That number? Or no, 0.
1.
1, yeah, exactly. So 1.393 to the 0 is equal to 1. And so it's 28 times 1, which is just 28. Yep, so anything raised to the 0 is 1. Anything raised to 1 is itself, right? All right, and the next, let's do it. Let me not spill this in anything. All right. So f of minus 5. We talked about negative exponents a little bit last time. So 28, and I'll just plug it in, 1.393 to the minus 5. And so remember, a negative exponent just means that you're putting whatever you're taking the exponent of in the bottom, in the denominator, and negating the exponent. So if you wanted to, you could rewrite this, and I'll put it down here. You could rewrite this as 28 times 1 over 1.393 to the 5. So all the negative is doing is it's popping it into the denominator. Now for us, as far as computing this goes, we don't really need to know that. But just remember that that's what it does. It will be handy later on, maybe if you take more algebra. Yeah. But as far as we're concerned, we can just plug this in our calculator. And I think just be careful plugging it in, right? So you always want to tread lightly when we're doing exponents. So I'm going to 28 times, so I'm going to do 1.393, then caret to the minus 5. And I always like to put extra parentheses, so I'm going to put parenthesis minus 5. Right? And I get that. So, and all round, 5.34. Right? Now, some calculators, you don't need to put the parentheses. Like in this one, I probably could have got away without any of these parentheses. But you can't have too many parentheses. It can't hurt. And it's always good to just to clarify what you want the calculator to do. All right, questions so far? All right, and then the last one is probably the simplest one, f of 16, because it's a positive power. Nothing tricky is really going on. So I get 28, 1.393, and then my x is 16, so I plug in x equals 16. And there's nothing I can do to simplify this. It's just, you're just plugging in a calculator. So let me do that. There we go. So I get 28, and then again, 1.393 caret 16. Right. So I get, it's a huge number, 5628.28. All right, so just some computation. Again, make sure you're comfortable plugging in these kind of things in your calculator, because we'll be doing it a lot. There's some of it on the homework. That's what we need to do. All right, so we're kind of back to where we ended last time. So last time, and this we talked about this last time, but I just want to review it again. So because this is the important formula here that we'll use for the rest of exponentials. So if R is the percent growth or decay rate, again, in decimal form, the exponential function can be written as follows. So in this case, where it's 1 plus R, is it growth or decay?
Growth.
Growth, yep. And then necessarily 1 minus R is decay. Now, usually it shouldn't be too hard to kind of remember which is which, right? Negative usually you associate with decay or going down, or negative bad things, and then positive you usually associate with good things like growth. So it shouldn't be too hard to remember which is which. But let's look at just how we can interpret some functions and using these equations, because again, these equations will be vital anytime we do anything with exponentials. It will involve these two just about. So for this first one here, and for all of them actually, I want to complete these missing values. So for the first one, I give you the function, and I want to talk about the initial value, the growth or decay, which it is, and then the rate at which it's growing or decaying. Right? So I should note here that this P naught is the initial value. So that's what your function will start at. So if you're modeling a population, you plug in t equals 0, which will correspond to 0 time. Your function will start at whatever this P naught value is. So if it's 100, your population will start at 100. If it's 504, your population will start at 504. Right? So in this example, what is my initial value?
100.
100, yep. All right. And then is this function growth or decay?
Growth.
Yes, right? And so it's growth because even though it's not written exactly like this, you can rewrite it, and maybe I'll do it off to the side here. I can write it as 100, and then it's going to be 1 plus 0.2 to the t, right? So my R here is 0.2. And since it's positive, that means it's growth. And then I already kind of told you that next part, my little r is 0.2. And as a percent, what is 0.2?
20%.
20%, yep. And you can get that just by multiplying it by 100. Right, so again, if it wasn't clear, that was 22.2 times 100. All right, next one. What's my initial value?
400. Yeah,
Sorry?
that right there.
That number, right? Yeah, 4,340.
Brain fart.
It's just that part one there. Is it growth or decay?
Growth.
Careful. So if I rewrite it in one of these two forms, right? So I'll write 4,340. And then
Since the decimal is less than 1, doesn't that mean it's decay?
exactly, yeah. And so again, like it has to be one of these two forms, right, to figure out if it's growth or decay. And so what you can notice is that they both have 1 plus R or 1 minus R, plus or minus, right? And so basically you're starting at 1, and your R is either going to add something to 1 or subtract something from 1. If you're subtracting something from 1, then you're decay. And so in this case, since I'm less than 1, I have had to have subtracted something. And so in this case, it's 1 minus, and then you do a little math, right? So if I do 1 minus 0.54, it's 0.46. So that must be what my R was. Right? So that makes sense. So again, I'm just rewriting it in one of these two forms. Since my thing inside the parentheses is 0.54, which is less than 1, it had to be the second form. And so to get little r, I just figure out what I need to subtract from 1 in order to get 0.54. And then, like I said, my little r is 0.46. And so as a percent, what is that?
46%.
Yep. All right. So questions with those two? So here you're given a function and you're asked to extrapolate the data that goes into that function. For these next two, it's kind of the opposite. We're given some data and we're asked to construct a function that models it. Right? So this next one here, we're going to be growth, and our initial value is 2.31. So if I write f of x, it's going to be my initial value, so it's 2.31. And I should have given myself more room, which is a recurring problem. And I get whatever, I'll just put it down here. All right. And then my percent, my growth rate is 6.4, right? So that's my little r, but it's percent. And if you go back to the formula, it has to be in decimal form. So remember, percent just means 1 over 100. So to get it as a decimal, I just do 6.4 divided by 100. So it's 0.064. So that's my little r. And it's growth, so I'm adding it on. So it's 1 plus 0.064, and then in this case to the x. All right, so questions with that one? All right, and the next one is similar. So I'll put it down here because I'm kind of, oh, that was a mistake, wasn't it? That's, it's okay. I'll put it over here. So f of x equals, so again, my initial value is 985, so I put that first. I'm decaying, so it's 1 minus something. And then my little r is 17%. So to get it as a decimal, I just do 17 divided by 100. So it's 0.17. And that's all my components. So then it's 1 minus 0.17 to the x. And you can leave it like that, like I did there, or you can simplify it if you like. All right, so any issues going back and forth? So ideally, you should feel comfortable either given some kind of formula exponential function like that, you should be able to go and find what the initial value is, what the growth rate is. You should understand how to plug in values, that kind of thing. And then oppositely, given data, you should be able to construct a model that represents that growth model, right? All right, anything? All right, so I made a note to myself here, do other examples. Now I wanna go back to the notes we ended on Thursday and finish. There was a couple examples that we didn't finish. So let's see, put this here, put that there. And so on Thursday, we ended here, all right? And so we did this little problem, suppose the population of ants grows by 50%. I won't redo it, but I'm gonna do this next one, which is similar, all right? So you have a substance that naturally decays. And so you wanna look out for words like decays or grows, because that's going to tell you what function you're going to use. In this case, since it's decay, that immediately tells us that we're using the second function. All right, so maybe I'll just put it down here. P of t equals P naught 1 minus R of t to the t. Right, so we know that immediately based on that function, right? That word right there. That naturally decays by 2% each year. And so this is something, we're not going to do it too much or at all really, but if you take more like pre-calculus or calculus courses, you'll talk about half-lives, or in chemistry, you'll talk about half-lives. And so some substances decay 50% or some number of percent each year, just kind of by chemical something or another. So in this case, our chemical substance decays by 2% each year. And again, that just means that 2% of the substance breaks down molecularly and essentially disappears. It becomes other things. How much of the substance will you have in 10 years? All right, so I don't give you an amount, right? So we can leave P of P naught, we can just leave as a variable. I don't give you any value, so we can just leave it as it is. And so we know it decays by 2% each year, so that's my little r. So little r equals 2%. And again, you convert that just by dividing it by 100 to decimal, 0.02, right? So I plug that in. So I get P of t equals P naught 1 minus 0.02 to the t. And as I said before, you can simplify that if you like. In this case, it's P naught, and then what is it? 0.98 to the t. And now what do we do to find out how much of the substance we'll have in 10 years?
You put that where the T is.
Plug in 10.
Yep, exactly. So t is time, right? So I plug in t equals 10. So P of 10. And this is just like we did in those first two examples in that quick review. So it's going to be P naught 0.98 to the 10. All right, so 0.98 and then caret to the 10. And again, you can round, unless I say specifically, or on the homework, we'll often say what to round to, but otherwise you can round to whatever. I usually just do 2 points, those would be 0.82. So P naught times 0.82. Right. And so the way you can read this, so again, I didn't give you P naught. If I had given you 100 grams maybe for P naught, then you would have 100 grams times 0.82. So you'd have 82 grams left after 10 years. But the other way you can read this is I can write this P naught times 82%. So what you can answer this by saying I'll have 82% of my substance left after 10 years. Oops. I'll have 82% left after 10 years. Okay. But again, if I had given you a particular number for P naught or initial value, you could just plug that in as well. So any issues there? Again, we're just identifying the variables and the formula from the word problem here. All right. So let's just try another one. Because again, this is the kind of core kind of problem we'll see in this section. So a city has 549 people living in it in 2009. If the decay rate is 16%, what will the population be in 2021? So here we have all the information, right? And I tell you it's decaying as well. So we also know what the formula is going to be. It's going to be P of t, P naught, 1 minus R to the t. In this case, I give you the population already. The initial population's 549. And the decay rate is 16%. That's my little r. So I can plug in P naught 549, 1 minus R to the t. And then little r, I'll put it over here, as I said, is 16%. But as a decimal, that's 0.16, just by dividing it by 100 again. So altogether, I get 549, 1 minus 0.16 to the t. All right. Now, this one is a little trickier because in the other problem we just did, I asked you how much you'd have left in 10 years. So there, it's really obvious that you just, or it's more clear that you just plug in 10 equals t, right? But in this problem, I'm giving you years. So basically, I'm saying it's 549 in 2009, and I want the population in 2021. So what do I plug in for this? What should I plug in for t?
2?
What?
2. Never mind.
You're close.
Whatever 2021 minus 2009 is.
Exactly, yeah. I think whoever said 2 was,
No, I thought I was thinking that it said 2011 because I didn't see the 2.
Exactly, yeah. You had the right idea. So basically you take the difference. So in 2021, there will be, so it's going to be P, and I'll just write it out. So it's going to be 2021 minus 2009. Right? And so what is that, 12? And now you plug in 12. So I get into the equation that we found. So it's going to be 5, 4, 9, 1 minus 0.16 to the 12. And you can simplify this first if you like. So 1 minus 0.16 is 0.84. So I can plug that in. 5, 4, 9, 0.84 to the 12. And then we're golden from there. Then I can just plug in the rest. There we go. So 5, 4, 9 times 0.84 all to the 12. So I got that number. 67.675. People. And fractional people are always odd. So you need to decide if you want to round up or down. I think rounding down makes the most sense. So we'd have, somebody else say, so we'd have, so there will be, say 67 people. But so the key takeaway with this problem is, again, is this indexing. So basically the idea is that whatever your initial population is t equals 0. So if I put in 549 here, that's setting my start year, t equals 0, to be 2009. So that's true whenever you use this equation, whatever your initial population is, or whatever your initial value is, that time will correspond to t equals 0. And so everything will be offset by that accordingly. Right? Does that make sense? So just keep that in mind. T equals 0 always corresponds to this initial value. So whatever that is, years, whatever, that's what you'll start at. All right. Any questions? Awesome. All right. I want to do this one. We'll save this one to the end. Let's see. Yeah, I'm gonna come back to this one. I'm gonna go back to these now. So this problem here is kind of like the population project. So I want to do this one right before we start talking about that. All right, so what's the type of bacteria? Triples every second. Find a formula modeling the population of those bacteria if there are initially p naught many of them.
What page is that?
This is page 4 on the notes I posted today.
Okay.
Yeah, sorry about that. And I'll be like writing these new notes, and I'll be like, I should have put this in. So I'm like, oh, I'll just go back to it. But then it kind of makes it a little messy. It's like a Back to the Future kind of thing. All right. So suppose the type of bacteria triples every second. Find a formula modeling the population. So so basically the question is, I know my p naught is p naught. It just wants me to leave it like that. But the question is, what's my r, right? So it triples every second. So if I draw a little picture. So that's one bacteria. And it triples. So the next second, I have 3 of them. This guy like splits into 3 maybe. All right, it's 3 bacteria. And this continues every second, all right? So maybe this is t equals 0. This is t equals 1. Second, right? So the question is, what is my R, right? I really want to know my R, my little r. If I know my growth rate, then I'm done. Any ideas what my little r is going to be?
3.
It's going to be 3. So, but you want to interpret it correctly. So, so you know that your little r as a percentage is how much your population of bacteria, in this case, are growing by, right? So if I start with 1 and I grow by 2, then I'm growing by 200%, right? Because so if I grew by 100%, then I would have 2 bacteria, because this 1 would be the same, and then I would add 1 more, which is 100% of the original. But if I'm going by 2, I get 2 extra. So you can think of this one as kind of remaining the same, and I add 2 on. So it's 100 for this one, and then another 100% for this one. So it's 200%. So this is 200% growth. Does that kind of make sense? Again, the way I kind of remember it is that I remember that 100% growth is doubling. So if I grow by 100%, then I'm adding on what I had initially. So I'm adding on 1 bacteria, right? And then the next second, I would add on 2 bacterias. All right, but in this case, I'm adding on double what I started with, so it's 200. In that case, though, that just means my little r is 200%. As a decimal, that's just 2. And then we're good to go. And so P of t, as I said, P naught, we'll just kind of chill. 1 plus r to the t. I plug in my r's 2, so I get P naught, 1 plus 2 to the t. And so that's just P naught 3 to the t. Right? So they don't, basically, you know, your little r doesn't always have to be really tiny. Like in the, you know, a lot of times with population examples or radioactive decay or something, you'll see like a really, really tiny r, like 1.3% or something small, but it doesn't have to be. It can be big. Like it can be hundreds of percent. It can be 200, 300%. And when you have bigger percentages, that corresponds to doubling or tripling or more kind of growth. All right. So just keep in mind, you can have r really be anything. All right. Cool. And then just a few more. And then we'll talk about the project. All right. So there's a question like this in the homework, so I wanted to make sure I covered it. There are 2 projections for a certain population. One is projecting 2% growth, and the other projects 7% growth. If the initial population is 100, provide functions modeling these populations. And what I want to do here, more importantly, is graph. Initially, I gave you like 2 kind of sketches of what exponential functions look like. But here, I want to show you how they relate based on the growth rate. All right. So let's just write out the functions, and we can do that pretty quick at this point. So maybe I'll say, so 2%, and what's the other one, 7%? I'll just put them next to each other. So P of t here, and maybe I'll say P2 and P7 t. All right. So what is my 2% growth function going to look like? What's my P naught going to be? Or my initial population?
100.
Yep. And then what am I going to put in parentheses? Anyone?
0.07.
Yeah. It's going to be 1.02, right? And then to the t. Right, so this is just 1 plus 2%, right? And then this other one's gonna be similar, it's gonna be 100, 1 plus 7% to the t. And again, you don't really want to leave anything like 7% in kind of an equation because that's really funky looking. So you just write it as a decimal, 100, 1.07 to the t. All right, anyway, so we've done that a few times now. So hopefully this is kind of working for you. But as I said, the interesting part with this one is graphing them. So I'm not going to do it with a grid or anything. Although I will say I did download grid paper. So the next time we have to graph anything with grids, there will be a grid in here for the person who commented. But we want to graph them now. And so they both start at 100, right? When I plug 0, t equals 0, and I'll put P of t there. Whenever t is equal to 0, right, in either equation, this part becomes 1. So I get 100. And then for this one, this is also becomes 1. So I get 100. So they both start at 100, regardless of which one we're working on. But one's going to be on top of the other. So which one's going to be higher? Would you guess?
7%?
The
7%?
2% one.
So the
2% one.
the 2% one will be lower, right? And the 7 will be higher because the 7s, every year you go, the P7 is growing by 7%. So for instance, in the first year, I gained 7 people. In the second year, I gained somewhat more than 7 people. But in the first year for P2, I only gained 2 people because 2% of 100 is 2. So basically, if you wanted to plot them, you could, but you'll find that P2 will be below P7. And so it'll kind of look like that, and then like that. So maybe I'll put P2 and then P7. All right, so P7 will grow faster than P2, all right? Because 7% is bigger than 2%. Is more than 2%. Okay. And what's important here is that the initial population is the same for both, right? So if we're comparing 2 different models for 2 different cities, and the population of city A was different than the population of city B, I couldn't say this kind of thing. But since the populations are the same, they both start at 100, I can say that since 7% is bigger than 2, it's going to be growing faster because the initial populations are the same. Right? They like the same reference point. Yeah. And so in the homework, they ask you to kind of, I think, put some functions in order based on the R, the growth rate or decay rate. And you want to kind of do it like this. You want to see which is bigger. And that will tell you which is above the other function. Is this kind of make sense? Is it okay? Is that good? Right.
It makes sense now, but as soon as I go to do the homework, it's gonna make no sense to me.
That's okay. You know, if you're doing the homework and you get stuck, feel free to send me an email, and I can answer over email, or we can Zoom, even if it's not a Tuesday or Thursday. I mean, assuming it's not like an odd hour of the night or something, I can probably Zoom you quick, regardless. So just let me know if you're really stuck. Just we can Zoom, have a quick Zoom. All right, cool. All right, and this next one is also a little different. This one we're gonna kind of play around with the T value. So an investment is initially worth 10 grand. Write a formula for the value of this investment if, and they got 3 cases, and each case is gonna be a little different. So the value increases by 5% every year. Right? And so this one is like our regular function that we've been doing this entire class and part of last class. So again, T is usually in years. So I'm gonna start my function, P of T, P naught, and it's increasing. So it's gonna be 1 plus little r to the T. Right? And so for this one, since it's increasing by 5% every year, I just plug it in normally. So P naught was 10,000. And it's 5% for little r. So it's just 1 plus 0.05 to the T. Right? That's it, right? Nothing fancy going on there. But for part 2, it mixes it up a little. So what's different here is that the value increases by 5% every 3 years. I'll put another line under it.
3 by 5?
Sorry?
It says every 3 years, so could you divide the 0.5 divided by 3 years?
That's a good guess.
0.05?
That's so there's a situation where you do that, and we don't do it until later. I think it's unit 3. It's compounding interest for us. So we will do something like that later on. But in this situation, what you want to do is so it's P of T, so P naught, 1 plus R, and so if it does 5% every 3 years, and I know that. So this is 5% every single year, right? So what I can do is I can just do T divided by 3. And so what it's doing is it's spacing out, basically spacing out this function over a longer period of time, right? If you divided the R by 3, I don't know if, I don't know exactly what would happen if you divided the r by 3. I think that would correspond, it's a little weird. So this is really an aside, but there's another formula. What is it? It's like P naught, and again, we'll do this later with compounding interest. 1 plus r over m to the t. So this is a formula for compounding interest where t is time again, so in years. M is the number of times it compounds every year. Number of times it compounds. You compound every year. And R again is the rate. So if you put the 3 down there, it's almost this compound interest formula, but it's not quite because you're missing it up here as well. So I don't know what that would model. It would be almost compound interest. Anyway, we'll cover that later in the semester. But anyway, this is what you would do for every 3 years. And again, the idea is that you're stretching it. So you're using this model where it compounds once a year at 5%, but you're just taking it out and you're saying, oh, it's doing it every 3 years now, right? And this one, we start with the same core model. Oh, and this P of T here, sorry, is, you know, you can finish this. Maybe I'll finish it. I forgot to finish it. So it's 10,000, and then 1 plus 0.05, and then T over 3. All right, sorry about that. And this one is again, same core, P naught, 1 plus R. But now, instead of stretching it out every 3 years, I'm doing it twice a year, right? I'm doing it every 6 months. So instead of dividing it by 3, what do you think I'm going to do to the t?
Multiply it.
Exactly, right? What am I going to multiply it by, Jim? Multiply it by?
2.
Yeah. So 2t. All right, so every 3 years, I divided it by 3. Twice a year, I multiplied it by 2. And so this is kind of an ad hoc, or we're kind of just playing around with the function. There's not really any rhyme or reason. There's not like a strict set of rules for doing this. It's based entirely on the context. But anyway, 10,000, 1 plus 0.05 to the 2t. Okay. We're kind of doing it by observation, right? You notice if I put 3t in here, I get exactly the first function where it was done once. If I put 1 in here, you'll notice it gets done twice. Because it happens every 6 months. So you're just trying to make a function that kind of fits the situation that you're getting, right? So again, this is kind of a weird problem. I don't know if this is on your homework, but I saw this example in the textbook and I thought it was kind of neat. So here we go. All right, so I think at this point you can do all the questions on the homework that's due Friday. Again, feel free to email me, or if you have any questions that you want to cover on Thursday's class, shoot me an email, and I can just go over them in class too if you're more comfortable with that. I know some people don't like Zooming individually, but finally, let's just do this one last question, and then maybe we'll talk a little bit about the project before we end class. So, suppose a town has this population data, right? And I just made these numbers up. Oh, and this is page 9. I think this is on the notes from Thursday. So suppose the town has population data, 2000 with the year and the population, and it seems to be growing, right? So if this data is growing exponentially, what would the growth rate be? What should the population be in 2022, right? So basically the idea is that you have some data and you want to find a growth rate R that fits it. And so what I'm going to do is I'm going to look at the relative change from each year to the next. So I'll make a little chart here. Relative change. All right. So for the first year, we don't have a relative change, right? Because there's no initial value to compare it to. So it's kind of like the chart we made initially way back Thursday, way back. But for the next one, I can't. So for the next relative change, again, it's going to be the new minus the old. So I'll put that up here. New minus old, all over old, right? So my new here is 2001, and my old is the population 2000. So I'll do 1, 3, 3, 2, 1 minus 1, 2, 1, 4. All over the old population, 1, 2, 1, 4, 1. Right? And then I'll plug that in my calculator and see what happens. So 1, 3, 3, 2, 1 minus 1, 2, 1, 4, 1. And divide that by the initial population, 2000, just 2000. So 1, 2, 1, 4, 1. And then I'll get it as a percentage, because usually it's more pleasing when it's a percentage. So times 100. So it looks like it's about 10%. Well, I guess I'll leave it as 9.72 maybe. I'll be a little more exact. All right, so now I'm going to do that just for the next few and see what happens. So I'll do 14,699 minus 13,321 over 13,321. Right. So again, I'm just doing this value minus that value divided by that value. So 14699 divided by 13321, and then divide that 13321, and then times 100 again. So this is about 10.34. All right, and so we don't really have an exact pattern yet, but it seems to be around 10. And then I'll do 16203, and I'll stop rewriting it all out so it's a little neater. But again, it's the value of the next year minus the value in the previous year divided by the value in the previous year. So 16203 minus 14,699 divided by 14,699. So, and then times 100. So I got about 10.23%. And I'll just finish it out. 17,982 minus 16,203 divided by 16,203 times 100, 10.978%. And then one more, minus 17,982 divided by 17,982 times 100. So this one's like, I don't know, 11.23%. All right, so in any case, so you'll notice that the percentage, the growths aren't all the same, right? This one's 9.72, this one's 10.3, 10.4, and they seem to be going up for some reason. But the point is now, I can kind of take an average of those, or I can just guess, right? So like you can say, oh, they're all about 10. So I could take R equals 10%. Does that make sense? And so basically I'm just saying, oh, it seems that the relative change for each year seems to be about 10. And so if I want to find a model that vaguely fits this data, I could take that. So it could take 10%, R equals 10%, and get a model vaguely fitting data. And so I'm not like, there's not going to be a perfect function that fits it. So if you, in high school, many of you probably did a function with these calculators where you had a bunch of dots, right? And then you try to find a line that best fit them. And so it's very similar to that idea. We're just trying to find an exponential growth function that best fits these data points. And the way we're doing it, there's a lot of more precise ways, but the way we're doing it is we're just kind of doing it by eye, kind of seeing what an average would be, right? So 10% would work. If you want to be more precise, you could take an average. So alternatively, could take an average of the R's. And so for instance, if I did, so let's see, 9.72 plus 10.34 plus 10.23 plus 10.98, finally plus 11.23. And then I have 1, 2, 3, 4, 5 of them. So divided by 5. Oops, shoot. Times 2 divided by 5. It looks like I have about 10.5. So it could take R equals 10.5%. All right, so either these R's would give you a decent value to model this population. So P of T, I'll do my average one because I think it'll be a little more precise. So it'll be, my initial population is 12,000, 141, 1 plus 10.5% to the T. Oops, sorry about that. And so explicitly, this is 12141, and then what is that? That's going to be 1.105 to the t. And so that function will kind of model the data I give you. And so if I want the population in 2022, I just plug in 22 for t because it starts again at 2000. So I'll do it down here. So p of 2022 minus 2000 equals p of 22. And so this is 12141 and then 1.105 to the 22. So some of these numbers aren't very pretty, but the reason I chose kind of gross numbers is because on the project, you're gonna have kind of gross numbers. So 12141 times 1.105 to the 22. So it's huge. It's a big number. All right. So it looks like it's 109,200. I'll round off the decimal. Okay. So again, exponential functions grow really fast. So if this population is growing by 10% each year, it's going to balloon. And that's why in 22 years, it goes up to 100,000. Okay. Any questions? All right. So,